6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13. 157.6 million pounds of thrust, and it has cleared the tower.
Prepare yourself for a world of science. This is Science.
What's going on, everybody? Conley here with the Science Nights. Dr. Thomas Schiller, Dr. Anirban Bhattacharjee, and Dr. Sean Graham here in the house. We have a very special guest today. We're going to be talking about Venus, our next door neighbor. Something interesting that's going on. And there has been a paper just published recently, and we have the honor of having one of the authors of the paper on the show with us. Sukrit Ranjan is here in the studio with us. Sukrit, how's it going, man?
I'm doing very well. How are you?
Oh, I'm doing great. Are you recording from Massachusetts?
No, I actually just moved to Chicago, so I'm calling you from my apartment here now.
Oh, sweet, cool. So Chicago, all right. So you're fairly, you're just kind of moving all around America, then, huh?
A little bit. I actually grew up around here, so it's a little bit of a homecoming for me.
Oh, wow. Yeah, I love Chicago, too. It's a great town.
Yeah, it's a lovely place.
Yeah, for sure. And we're really looking forward to having you on the show today. I particular am very interested, always with, as well as our listeners, they're very interested in understanding how life works, especially on other planets. And is it a possibility that this recent discovery that you and your team have made could, tell us a little bit more about life on Venus? And our own Anirban Bhattacharjee's here, physicist extraordinaire and astronomer.
So, Sukrit, I was going to ask you, you did your PhD from Harvard, right?
That's correct.
And you did your PhD also on planetary sciences, or what did you do your PhD on?
It's geared on the planet side. I think planets are super cool and super interesting, so that's what I've studied for a while. My PhD was focused more on kind of trying to understand the origin of life here on Earth and trying to understand how we might look on other worlds. And then for my postdoc, I moved a little bit after my PhD. For my next job, I kind of moved into trying to focus on understanding the interaction of UV radiation with molecules in the atmospheres of planets.
Okay, and then now you're in Northwestern in Chicago, right?
That's correct, yeah.
Yeah. So, and that's where you have, and you're only working on Venus, or are you just also working on other stuff other than Venus? And we'll come to Venus.
Venus was a side project for me a little bit. I mean, it's a side project that consumed our lives for about 6 months, but ultimately I think Venus is a very interesting test case. Yeah, my primary research interests lie elsewhere.
Yeah, you were part of a big team that has this gigantic, huge news announcement recently. The 6 months that went into this, that I'm always curious about that kind of stuff, like what all goes into a study like this. So that's 6 months of number crunching, kind of. What kind of stuff were you doing to consume your time?
Well, the story is actually quite broad. In a sense, the story starts. Depending on how you draw the circles, the story can start in 2019, as it did or it can start all the way back in 2016 or 2017, or if you could push really far back, it goes back to the 1990s. And in a sense, the story goes back. You can push it all the way back to the 1990s because that's when some of the first convincing evidence started coming in that showed that phosphates was associated with biogenic production here on Earth. That wasn't a gimme before then.
Oh, okay.
There was actually a series of pioneering papers by a guy named Glindem, a German chemist, I believe, who was doing some fundamental work there.
Interesting. And yeah, I guess at this point we should just kind of spill the beans to the audience of what exactly we're talking about. You guys found something very special in the atmosphere of Venus. And could you just give us a little bit of background?
I think we found something weird.
We hope so.
Yes.
But what is it that you did find? And tell us just a little bit about that.
So what we think we found in the atmosphere of Venus is this molecule called phosphine. Now, the way phosphine works is it's a single phosphorus atom that's connected to 3 other hydrogen atoms. So its molecular formula is PH3. Very simple molecule, very small molecule. But it's a really weird molecule to find in the atmosphere of Venus. The atmosphere of Venus has very little hydrogen, but it has a heck of a lot of oxygen. So if you stick just any other atom over there, like suppose you stick a carbon, you expect it to mostly form CO2 because there's a lot of oxygen running around there. If you stick nitrogen in there, well, you don't expect nitrogen to do much anyway, but if it was going to bond with something, you'd expect it to form NO species, not NH species. Similarly with phosphorus, if you stick a P in there, you kind of expect it to form, to bond with O's and make oxygen-containing species. But what we seem to have found here is phosphorus bonded to hydrogens, which is really unexpected. And the kind of special thing that, as you point out, that we are finding there is that, well, we scratched our heads and we're like, well, what can put it there? And we have a catalog of things that we know to look for because scientists led by NASA, among others, have put a lot of effort into kind of establishing a catalog of processes you can check when you find something weird. And so far, at least according to our analysis, we've drawn blanks. The stuff that we know about, like lightning, like volcanism, like delivered from meteorites, can't explain the signal at the abundance we've seen it. They can produce small amounts of this molecule, but not quite enough to explain the abundances we're seeing.
So bringing it back to phosphine, right? So if you want to describe the atmosphere of Venus, what would you say? We know our atmospheres have layers, right? How many layers of Venus would you say are there, like the primary layers in Venus's atmosphere?
That's another really great point. The atmosphere of Venus is very, very thick, and it's in some senses very diverse. Of course, the upper part of the atmosphere is like our own upper part of the atmosphere here on Earth. It's cold and thin. It's actually a little bit colder than it is here on Earth because of the radiative properties of carbon dioxide in that region. And then the bottom of the atmosphere is the polar opposite. The atmosphere is very dense. You have 90 times the surface pressure you have here on Earth. And it's very, very hot. It's over 400 Celsius. It's hot enough to melt lead.
Yeah, that's one of the big surprising things about this find, right? Because a lot of people who are like planetary nerds know a little bit about planets have kind of forgotten about Venus. We're like, no. The pressures on the surface, the heat on the surface. I guess the Russians landed a spacecraft on the surface and it practically melted right on the spot.
Yeah.
So it's a terrible place for life. No way. But
absolutely,
the middle atmosphere, right? You were just about to describe it. The middle part of the atmosphere
seems to be kind of spanning that transition. So the middle part of the atmosphere, it's still a hostile place, but it's perhaps not quite as hostile as either extreme. In the middle part of the atmosphere, we've observed decks of clouds there. Clouds where you do have some liquid water present, and the temperatures are between the freezing and boiling points of water. And you also have the presence of some fluxes of some some of the basic bioessential ingredients you need. And so it's been suggested that if you're going to find life on Venus, life as we know it, the cloud deck isn't a terrible place to look. It's probably the most likely place to look. And then some people will jump right into saying that they're habitable. The cloud decks are habitable. I'm not sure if I would push that far. The cloud decks are made of 90% sulfuric acid, and any biochemistry as we know it would just kind of melt there.
That's what. Go ahead.
But I think what we have to say is that we've frequently in our history of studying life here on Earth, we've often established boundaries that life can't be found here. Like we've said that life can't be found in very hot places, and then we found it in very hot places. Life can't be found in very salty environments, and we found it in salty environments. So I think a lot of us who think about habitability think that, well, maybe we don't know as much about how life works as we think we do, and maybe it's up to us to read the book of nature and understand what the fundamental limits on life are. And I think the reason for being open-minded about the existence of life on Venus is that the one thing that we almost everyone can agree on is that life requires liquid water, and that at least does seem to be present in the Venusian atmosphere and that cloud deck. So that's what kind of lets us open up the possibility, the remote possibility, that maybe this is an option we should consider as well.
Okay, and I was just going to say, and what about the pressures in that middle layer, like that temperate layer out there?
The pressures aren't too extraordinary. Fundamentally, pressure is not that big a barrier to life as we know it, in the sense that even at very, very high pressures, enzymes still work. Like at the bottom of the ocean, you still have life functioning. So high pressures in and of themselves aren't a barrier to life as we know it. The big problems for life as we know it in the Venusian clouds In my opinion, the two big ones are, the biggest one is all that sulfuric acid, which is just a very hostile environment. A month ago, I would have also have highlighted the very small amount of water, what's technically called low water activity, is another major barrier. But after we published our paper, some folks reached out to us and were telling us that we are not up to date on the literature, that they've cultivated microbes at much lower water conditions than we were aware of.
Wow.
So maybe that's not as fundamental a barrier as we were talking about. So going back to nature teaching us more than telling us that we don't know as much as we think we know.
Yeah, I like that.
So I'm the biologist here, and I should know this, but I don't, and I'll bet you do. So sulfuric acid, there's a lot of bugs on Earth, the extremophiles, these little bitty microbes that can break down chemistry of kind of bizarre types of chemical, make bizarre types of chemical reaction and actually get energy and carbon from weird chemistry. Are there microbes on Earth that can make do with sulfuric acid?
Not at this concentration, no. Yeah, the sulfuric acid abundance is just too high. I think if you project it to a conventional pH scale, it's about 10 log units more acidic, so it's like billions of times more acidic.
Oh my God.
It's a totally different biochemical regime.
Yeah.
If something exists there, it's evolved a very different biochemistry, or it's using some kind of alternative scaffolding.
Yeah.
Wow. As far as the density, like for our general audience listeners, some of them would like to know what the density of phosphane is, and does it settle in the atmosphere under certain surface conditions? And does it like other molecules next to it, near it?
Those are all great questions. So phosphine, we argue that we've detected it at a concentration of 20 parts per billion. At an altitude of around 50, 60 kilometers or above. We aren't able to constrain how much or how little there is of it at altitudes below there. But our guess going into this is that there shouldn't be very much down there, but our guess was that there shouldn't be very much up there either. So what do we know? And the fundamental reason for that is that phosphine is not a very stable molecule. It's really easy to destroy. It's very vulnerable to UV photolysis. It's really vulnerable to reactions with what we call radicals, reactive species that are present in most planetary atmospheres. So it falls apart pretty easily, which is why, again, we're a little bit surprised that it's there in an environment like Venus's.
So if I was to have, like, let's say, for our audiences to have a picture, like, let's say I have some amount of phosphine sitting out there in just normal atmosphere on Earth, right? How soon would it, change into something else?
So first off, you're going to go to prison because
okay, good.
It is violently toxic. It's a very much controlled substance. Some of its industrial applications are basically for poisoning mammals. It's used for, I think it was famously used in the TV show Breaking Bad. I think the protagonist used it to harm some folks.
Like meth or something?
Rats
Don't get any
like
ideas,
Anything
listeners.
that uses oxygen, any life that uses oxygen like us, it's a very, very bad story for it. The only kinds of life that seem to generate it are those that are environments that lack oxygen because they don't have the same biochemical pathways that phosphine attacks. So we're talking about wetlands, the core of wetlands, which are anoxic, the intestines of animals, that kind of places. So let's get over that issue and suppose that either you bought off the local inspectors or you set up,
talk to Walter White a little bit.
Yeah, you set up a sterile environment someplace where you're protected and everyone's super safe and it's isolated. Phosphine on Earth is going to fall apart really, really quickly. For a similar reason to Venus, Earth has a lot of oxygen. And when that oxygen interacts with UV light, it's going to produce so-called oxidizing radical species. And those oxidizing radical species, like OH, will attack that pH3 and destroy it very efficiently. That's why pH3 is pleasant. It's mostly not present in Earth's atmosphere at all. You only find it over where it's produced, places like penguin colonies, and even there in very low concentrations.
So for us to have something like on Venus, for you to observe it, something must be producing it, right, in some certain amount of quantities, because it's getting destroyed pretty rapidly, even on Venus, right? So
that's correct.
Well, what would be the difference between what you discovered on Venus and the phosphine that gets produced by volcanism here on Earth?
So first off, you have very little phosphine that's produced by volcanism here on Earth. And we're talking the bulk volcanism average over the entire planet. There are some special environments, some special volcanoes that are what we call very reducing, that they're very hydrogen rich, where you might have a certain amount of phosphine being produced. But if you look at the globally integrated production, it's basically zero. The geological sources due to volcanism are extremely minute, relatively speaking.
Wow, yeah, that's fascinating.
And we expect a similar picture for Venus. Now, one place in the solar system where you do have a lot of phosphine produced are the gas giants. Planets like Jupiter and Saturn, those big giants out there, which are basically all hydrogen. And even there in their upper atmospheres, you don't get very much phosphine. The phosphine that's there is dredged up from the lower atmosphere. In the lower atmosphere, you both have a lot of H2, a lot of hydrogen, and you have really high temperature and really high pressure. And the combination of those factors lets you generate phosphine deep in the atmosphere, from which it's then dredged up by atmospheric circulation, and then we can observe it with our telescopes in Jupiter and Saturn. But Jupiter and Saturn are very different from what we have here on Earth and even from what we have on Venus.
Now, I was curious about that because when your paper first came out, I went bananas and I was super excited. And I just went and looked up phosphine, and to see, I was actually trying to find your paper. I was trying to, use Google Scholar to find your paper, and I found all these papers about phosphine and gas giants.
Yes.
And I thought, well, that's how exceptional is this? And so the temperatures, you said hot temperatures, a lot of hydrogen. Now, Venus doesn't have a lot of hydrogen, but it's got hot temperatures and high pressures. But are they off the scale compared to gas giants? Way less or way more?
Yes. So let's ignore the question of hydrogen altogether, but you can't because hydrogen is the most important thing. In the gas giants, it's formed thermochemically.
Right.
And its formation is favored because you have such a high hydrogen activity. You have so much hydrogen around. So, but even if you ignore that, let's pretend that Venus's atmosphere was entirely H2. You're still not in the right range of the pressure-temperature diagram, where Venus, like more than 50% of the phosphorus, would be present as pH3 compared to PO4 compared to phosphate.
Right. So
the biggest barrier, I don't want to overemphasize the temperature and the pressure. I want to emphasize the hydrogen. The hydrogen is
that's
the bigger
biggest
barrier.
thing. Yeah. And so Venus's atmosphere is super rich in oxygen, very little hydrogen, and so that just doesn't add up. There's something missing.
And I just want to clarify, when I'm saying rich in oxygen, I'm not saying stuff that you and I breathe.
Right.
I'm saying oxidized species, like oxygen atoms, but not free molecular oxygen.
Right.
Sure.
Yeah, you mentioned that a second ago, and you said something about oxygen being similar in quantity on Earth, and I think some of the listeners might be thinking, wait a second, I thought the oxygen on Earth came from plants.
Exactly, yeah.
That's free oxygen. The stuff in Venus is bound up with other elements, and it's not free oxygen.
Exactly, yeah.
Like sulfuric acid in itself also has oxygen.
Right, there you go. A lot of it too, I guess.
That SO4, very oxygen rich.
Yeah. So thinking about phosphine and the molecular structure that you said, so it's being produced right now in the middle part of Venus. So, and when we would come back in the next segment, what I would like to go over is like, how did you guys manage to actually differentiate that your observations are actually coming from the middle part and not from the upper part of the atmosphere and the lower part of the atmosphere, because that's a pretty cool observational technique, and I bet that is also pretty challenging to do, right? I would assume that kind of observation.
Yeah. You want me to talk about that now? Or
well, no, maybe after the break, and we could also go over, with that, talking about the two different types of radio signals that was used to discover this as well, right?
Certainly, yes. And then
awesome.
I can talk to you about some new results as well.
Oh,
awesome.
Getting us all excited here. All right, well, we will be back after the break. Keep it right here, everybody. All right, everybody, we are back, and we have a very special guest. Sukrit Ranjan is here in the house and made a very, very important discovery that is making the science community really scratch its heads about how life is really developed, right, in general. And this next segment, we're going to be talking about some of the techniques that were used to discover this mysterious presence of phosphine in Venus's atmosphere, and also some of the instruments used. So Do you want to go ahead and ask that question you were asking before?
Yeah, I was just wondering, when Sukrit said, we discovered this phosphine in the temperate regions, right? And we also talked about that the Venus is an upper layer and a lower layer, right? How did you manage to know that this phosphine has been produced in that temperate layer?
That's another really great point. So, and here I'm going to have to give a disclaimer that I'm a theorist. I'm not really an observer, so I can't just give all the details, and I maybe don't know everything over here. But these are the same questions that I asked my observational colleagues when they told me this. I was like, how do you actually know this? So what I can share with you is what they told me.
Perfect.
What they told me is that, so the way you detect a molecule in the atmosphere of Venus or similarly planets, the surface of Venus is giving off radio waves. And some of these, if you have a molecule present, based on its molecular structure, based on its electronic structure, some of those radio waves in the atmosphere, it's going to absorb. And so it'll take away some of that radio light. And you can look for that dip in that light at radio wavelengths. And the molecule doesn't remove the radio light willy-nilly. It removes it at a specific wavelength. It removes a specific size of light wave. And so if you look, and the size of light wave it removes is characteristic of the molecule. It's like a molecular fingerprint. Mm-hmm. And you can use that to try to match which molecule is doing that. So you're looking for a dip in the light, but what are you looking at a dip relative to? You're looking at a dip relative to what we call the continuum. Now, the continuum, so you're looking for an area that's relatively flat, and then you see a little bit of a dip. The shape of the continuum and the amplitude of the continuum that we see the dip relative to is characteristic of the upper part of the Venusian atmosphere, around 50 to 60 kilometers. It's not characteristic of the lower part of the Venusian atmosphere. So we're not sensitive to anything in the bottom of Venus's atmosphere at the phosphine wavelengths. There could be a ton of it there could be none at all. We have no idea. The only area where we're sensitive to the phosphine is in the upper part of the atmosphere using this technique. But there's another technique which some clever people figured out, which we can get into later. And so that's how we're kind of localizing the signal. You might say, how do we know that it isn't all up in this super upper part of the atmosphere? The answer there is that there's just not very many molecules there. So it's got to be a little bit low, like in that region, it's got to be in the lower part of that. So that's what's in the middle as opposed to the very top.
Yeah, because what I remember, I have done observations a lot, but I haven't done observations of this type. So, and basically the strength or the amount of that dip will basically tell you, gives you an idea what's the amount of phosphine present in the atmosphere.
Exactly.
Right.
Yeah.
So, and that's how you calculate that 20 parts per billion, right? Billion. pp.
Yes.
Yeah, 20. So that's how you get to that. And I assume the reason it's kind of to do with we are not getting the lower atmosphere would be something to do with the sensitivity of that instrument, if I'm not mistaken. Or is it nothing to do with sensitivity? Because
to my understanding, it's not just sensitivity. At the lower part of the atmosphere is so thick, that it absorbs all the radiation coming off Venus and then re-emits it.
That's what I was thinking, and that's what it re-emits in the radio wavelengths.
So it reprocesses that radio, and that continues up until you get to an altitude such that the atmosphere above is no longer so thick as to completely reabsorb everything. Yeah, and that's where you get that phosphine signal.
Yeah, and basically what is happening that it's becoming kind of an opaque underneath that layer of atmosphere. We are unable to probe. So that's what is happening. Okay, so and that makes perfectly sense. That's what I was wondering, that why are we not getting? And yeah, as you said, it's completely opaque.
Crazy. It doesn't make any sense. I can't believe that we're observing this stuff with radio waves.
Yes.
Like I would have thought you talk about the electromagnetic spectrometry. Is that what
spectrometer?
Spectroscopy?
Spectroscopy is kind of what I was expecting him to say. That you look at the light and then there's these little kind of little dark spots in the light, and it corresponds to the different kind of chemistry, and that's how we know that certain stars are the different elements that they are. I was not expecting him to say radio waves. This is nuts.
Radio waves, like the thing we have to remember, it's the reason you have to use radio waves is the same reason we got to use radio waves for our Wi-Fi signal. It passes through most matter. It has a much higher transmission. And we have to remember that Venus's atmosphere is so violently thick. There's so many molecules. And not only are there so many molecules, but they also condense to form all these hazes and all these clouds, which are really strongly light blocking. So light like you and I see, or even the infrared wavelengths, are really strongly blocked. It's really hard to do those measurements. Actually, since this discovery, my colleagues have been leading efforts to follow up in other wavelengths, and it's just a lot harder than the radio. It's just they're having trouble. They're only being able to probe the upper part of the atmosphere, where you have less molecules and it's thinner. You don't have as much hazes and stuff.
Very clever, very clever.
And also, we have to, and you can say, why can't we use the longer radio wavelengths? But there is also certain other problems with using longer radio wavelengths. If I don't remember the top of my head.
We're talking about the difference between AM and...
There is like a frequencies of observation because you need to have bands and stuff like that. But... one of the interesting things about people forget about Venus is when you said that blocking the infrared radiation, everything, that's one of the reason is its atmosphere is so thick. That is the reason Venus is so hot inside.
Yeah, absolutely. It's got a really, really strong Venus greenhouse effect. Venus, we think, underwent what we call a runaway greenhouse, which is where it passed this tipping point, and so and it started getting hotter. And when it got hotter, its water evaporated. Water is a really effective greenhouse gas, so it heated the surface up even more. And then you had this runaway feedback loop, which led to the oceans boiling off, and that's what we think ended up lofting it into this state that we have here today.
That's interesting. And the fact that if that's the theoretical idea about the history of Venus, that means that life could have evolved on Venus under better conditions. And then that means that you got the potential for some little bug in the atmosphere that's a survivor. I feel the same way about Mars, that like if there was ever life on Mars when it was more habitable and there's still water somewhere on Mars, there's a really good chance it's still there. Because I feel like if the Earth turned into Venus... right? If the Earth spun away in a greenhouse nightmare.
We are trying our best.
Right. Or if
we're working on
if Earth 100 million years from now went the Mars way and became like the ultimate desert planet, something would survive. There'd be deep caves under ice lakes, and some of our microbes would survive. So I think that's cool that even though it seems horrible, that the presence of ancient oceans on Venus is kind of a good feather in your cap in terms of explaining how this thing came about.
Yeah, there's kind of 3 points I'd make there. One is something that's relatively recent, which is that, well, there's a few things. One is relatively old, which is that there's some evidence of this picture that I sketched out of runaway water escape in the enrichment of the so-called D/H ratio on Venus, which has been interpreted as a signal of its desiccation, that it did have oceans a while ago. And so that's an insight that's some decades old now. More recently, there's been a few papers which used 3D modeling, climate modeling, to argue that Venus might have been habitable quite recently, as recently as just 700 million years ago, which is a while ago, but relative to the age of the solar system, drop in the bucket.
Yeah.
So that's also exciting with that picture. And then the third thing that I'd point out is that one thing that fascinates me is the idea that, we have a lot of meteorites from Mars here. So we know that Mars has been sending us rocks, and we think that all the 3 terrestrial planets have probably been exchanging rocks throughout their lifetime. So it's not even necessary that life had to start separately in each of those worlds. It might have started in any one of them and spread to the rest.
Yeah, you can imagine.
You only need one origin.
If 700 million years ago, Venus, Earth, and Mars were all kind of Earth-like with oceans. Imagine that.
Wow.
And they're exchanging rocks through meteorite impacts.
As a planetary scientist, this couple of months has been pretty good, right? Like you had this your paper coming out, and then immediately people following up with finding out a bunch of lakes underneath the surface of Mars. And
were they trying to one up you, by the way? Is that that planned? It was like back to back 3 days later. They're like,
they're sandbagging it.
We want those BBC interviews. Come on, let's get this out there.
Well, I think it's just a really productive time. I think we live at a really special time in human history where we're exploring all these other worlds and making all these cool discoveries, both within our solar system and outside of it. I think it's a testament to what we've accomplished as a species and a people, that we're able to answer some of these questions and explore some of these questions now that we're out of reach for so long. And it's such an exciting time to be alive. I don't really think that there's a one-upmanship thing, because each of these discoveries is fascinating in their own way and worthy of investigation.
No, we were just joking, but bringing it back to Venus is like I was going to ask you, like Conley was talking about. So the instruments used were in, I'm assuming in Chile. You said ALMA, right? One of them.
Yeah. So the first instrument this was detected on was the James Clark Maxwell Telescope over in Hawaii.
Oh yeah.
And that was a very tentative detection. They thought it was there, but like there was a lot of noise that you could really argue with it. So then what they did is they went and they looked for it with another telescope, the ALMA telescope in Chile, which is much stronger and much better. And those data look a lot clearer. The signal to noise appears to be much stronger and a lot better. So that's that's kind of more a bit of a stronger evidence. Now you can still dispute the evidence of phosphine on Venus. So what this has done, the big problem is that we've only detected one spectral fingerprint. And the question you always have is, well, is there another molecule that could be masquerading there?
Mm-hmm.
So we looked at the molecules that we know about, and we tried to see the one that has the most risk of that kind of obfuscation, the most risk of kind of masquerading as phosphine is SO2. And they actually, my observational colleagues, this is why they're observationalists, they're very clever, it turns out. They had a clever way of trying to figure out if it was SO2 or not. They said, well, we know other features of SO2. Let's look for it. They didn't see it, and they were able to use that to say, well, the SO2 feature SO2 can't explain the whole feature we have, because if it did, we'd see it at these other wavelengths as well, and it's not there. But that still leaves open the possibility that there's some other molecule that we don't know about, or that one of the molecules we do know about has some absorption feature, happens to have that fingerprint as well, and we just don't know it. We haven't measured the full spectrum of all of these molecules yet. So, so we were kind of thinking we were going to be shot. Like we were thinking that the next big thing was going to be somehow detecting other fingerprints of phosphine at other wavelengths.
Okay.
And so that's what my colleagues set out to do, but it's been very frustrating for them, both because the pandemic has frustrated their observational efforts. It's been hard to get the telescopes running, and also because it turns out the other features just aren't as promising. A group led by some folks at Cal Poly had a really clever idea, which we hadn't thought about at all, and which might have its own problems. It hasn't been through peer review yet, but they posted a preprint earlier last week. Which is they went back and looked at the old Pioneer data. So the U.S. sent some probes to Venus that descended through the atmosphere. They have an instrument on there called a mass spectrometer, whose objective is to try to figure out the compositions of the what different gases they are made of. And they tried to look for evidence of phosphine in those data. And they claim that they have found evidence of phosphine in that middle part of the atmosphere as well.
Wow.
Okay.
So I don't know about mass spec. I don't know how strong the results are or not, but they put their preprint up, and I talked to them about it. I don't know. It sounds convincing to me. I don't know much about it. So
how cool! How cool that you would have like this confirmatory evidence from decades ago. You know, There's like an old saying, I forget how it goes, but something, there's no substitute for gathering great data, you know, and you got this spaceship you sent to Venus, you might as well try to get what you can from it. And it'd be really cool if that turns out to be an independent confirmation. How neat.
Wow.
Yeah, that would be really cool. We thought we'd have to wait decades to get in situ confirmation, and we never imagined that this might have been buried in the original data all along, but if we were talking to them, it looks like there's a lot of things buried in that original data.
I'm excited about that.
So this brings us like kind of before we end the segment, I was thinking to myself, like this at this point we have pretty much coming to one firm evidence there is phosphine in Venus's atmosphere, and with
not yet.
Strong
evidence is the burden of proof is on folks who disagree to disprove it, but that could still very easily happen.
Okay.
And I just want to emphasize the scientific community is doing a great job here. We've made all of our data public, and I'm aware of at least one, probably more initiatives to independently reanalyze the data.
Okay.
And see if they agree or disagree.
Okay, so that's good. And I'm assuming also there's going to be future observations that are going to be like follow-up observations.
Yeah.
Okay.
As soon as COVID lets us.
Yeah, we'll get definitely to that in the next segment. We have some questions for Sukrit. Real quick, we have about 4 minutes left in this segment. I want to talk about your team and how many colleagues are part of this project and part of this discovery. And you already described some of the challenges, but do you foresee any challenges in the future of making this hard evidence now?
There's a bunch of stuff to be done. The team was about 20 people, which sounds like a lot, but as for discoveries of this type, it's actually quite small.
Mm-hmm.
Actually, some of the flack we've gotten is for not having a bigger team.
So like people from WMAP or Planck missions, are they wanting something like that?
I think folks have. I don't know. We've just been told that we should have had more people on it. I don't know. We tried to just. We felt this was adequate for the work we were trying to do, but we'll see what happens.
These days, everybody puts about 100 undergraduate authors on their papers, so I was actually kind of happy to see that I'll bet all 20 of those people actually had a really big contribution, so keep that.
Well, I guarantee if you hint that there could be oil on Venus, that 20 would turn into like 20,000. I guarantee it. Just, you can embellish a little bit. But.
There you got Titan. Titan's got oil on it.
There we go.
We should go like mine Titan.
Let's go. Hey, I'm sure they're already in the process of finding funding for it. But, But yeah. Well, do you foresee any challenges to, continue the study before we get to our last segment?
Oh, I think I don't really see challenges. I just see opportunities. I think there's a lot of really great work to be done. I think there will be independent reanalyses of the observational data, and we'll see if the detection holds up to the scrutiny of the scientific community. There will be analysis now of these pioneer data and maybe some data on the Russian side as well from their landers to see if there's evidence of phosphine being present. So that's another thing that will happen. There'll be a lot of laboratory studies. People will try to figure out, because we don't know the chemistry of phosphine very well. We know its thermodynamics, but not its kinetics, not how fast reactions happen under cold conditions. And believe it or not, from a thermodynamic perspective, Venus is cold. So there'll be a lot of folks, there'll now be a lot of more support to do fundamental laboratory studies of the photochemistry of phosphine and its related molecules. And it might be that once we understand that better, we'll discover a new mechanism that efficiently synthesizes it under Venusian conditions. So we have more work we'll be doing with extant facilities and data to confirm whether or not phosphine is there. And we have a lot of lab work we'll be doing to figure out abiotic ways to make it. And if all that continues to hold up, then I think we have a case for trying to figure out, what is the phosphine production mechanism? And then we might start thinking about things like space probes and so on and so forth.
Oh,
but
man.
First, we have a lot of work to be done right here on Earth.
Yeah. That's really interesting.
Yeah, well, great. And that leads us, we're going to end this segment on that. Our next segment, we have a very important decision to make now. And we're going to go over to that right after the break. All right, everybody, we are back, and we have a special guest here, Sukrit Ranjan, here on that very, monumental paper about finding phosphine remnants of life on Venus. And we've been talking about that throughout most of the day. But, Sukrit, I do have some questions from our listeners. And one big question that I've been getting throughout the week this week is, we found some, I guess, what would you call it? Theoretical evidence?
Like strong evidence.
Strong evidence, saying that there is phosphine located in the atmosphere of Venus. Now, what should we do next? What should be funded first? Now, some folks have said maybe we should do a simulation here on Earth using my field, computer science. Guys, natural science guys. Anyway, but I'm still a lowly squire. I'm working on that doctorate. But anyway, should we do a simulation here on Earth that models phosphine in Venus-like environments? Maybe we should send out an entry probe to Venus to track the environment of its atmosphere, and then send data back, to us that way. What are some different ways or techniques that we can recreate the production of phosphine in this Venus-like environment to take the next steps into this discovery?
That's a really great point. So I'm going to focus on the question that you posed, which is methods of potentially producing phosphine under Venusian conditions, and I'm going to leave aside the related question we discussed before the break of how do you confirm phosphine is really there or not. So I'm going to ignore that question for the time being and focus on, let's assume that we're right and there is phosphine there. Mm-hmm. How do we figure out what's making it? I'm a computer guy myself. I'm a theorist. I do a lot of computer modeling, but I got to say theory is not the path forward here, because there's just too much we don't fundamentally know, both about Venus and about the chemistry of phosphine and its related molecules. You know, in order to simulate something in a computer, first you need to be able to describe its properties pretty well. You need to be able to build a good simulation. And right now we know some stuff about phosphine, although not super well. But there's a bunch of related molecules like pH2 or pH, and the crossing between the oxidized and reduced forms of phosphorus that we know almost nothing about. In our paper, we had to estimate those rates by analogy to molecules bearing nitrogen instead of phosphorus. And if any chemist out there is going to wince a little bit, it's the best we could do because we just don't have the experimental data. So if we're trying to figure out where phosphine is coming from, first and foremost, we have to do a lot of laboratory studies. We have to reduce the uncertainties. We have to measure those reaction rates. We have to measure other processes that might be creating phosphine, that might be able to create phosphine under Venusian conditions. So a lot of lab work first. Once we have that lab work, we can incorporate it into kind of into better numerical simulations of Venus and its atmosphere and see if any of those mechanisms can work. But even those are going to be imperfect because there's a ton we don't know about Venus's atmosphere. Our models can't reproduce something as basic as the water vapor concentration in its atmosphere at high levels. That normally has to be assumed. That's all models, pretty much, as far as I'm aware. So we need to understand a lot more about Venus. We need to understand a lot more about phosphine. A lot of that work can just be done in the lab right here on Earth. And I'm a little bit stingy. I like to think about how can you get the most science for the least expenditure. And that's actually a lot of like really high return science you can do, in my opinion. It'll take a little while. Maybe it won't be as exciting as sending a mission right off the bat, but I think there's a lot of, in my personal opinion, I think lab work is where you go for bang for your buck in the beginning. And then if that holds up, then you can design a mission to go and investigate Venus in general, and then a potential phosphine production mechanism on Venus in specific, once you know more about what's there and what you can predict and stuff like that.
I think that's fantastic. And I love, from the listener's perspective, I think this is a valuable lesson because a lot of people would assume that, they found a biomarker for something really cool in Venus. So I guess the next step is we're going to launch a rocket. Let's go let's send astronauts. Let's go for it. But you're describing systematically destroying your own possible hypothesis. You got basically two hypotheses. You got one that it's a bug, a microbe, and the other is that it's some sort of chemistry you don't understand. And you're going to systematically destroy one of the hypothesis that would be the greatest discovery of the century. That's what you're going to do first. That's the first thing you think of, and that's how science works, everybody. That's just beautiful.
And on the positive side, I was going to point out is like discovering phosphine, and if there is an abiotic process like which doesn't require any kind of living organisms, we would have discovered a completely new fundamental process. Am I right here, Sukrit?
Yeah, so I think as a planetary scientist, of course, finding life would be lovely.
Yes.
I don't think we're anywhere near there yet, but it's an interesting possibility to keep in the back of your head. But it's completely irrelevant to why finding phosphine on Venus, in my opinion, is so exciting.
Yeah.
The first and most fundamental reason is that it tells you that on rocky planets, you have to think about gas phase phosphorus chemistry. That's something that we've ignored. So before this, we were finding all these planets orbiting other stars. And I and others have been working on the process of simulating their atmospheres and figuring out, what are biomarkers on those worlds and what are markers of different geological processes on those worlds. And our models never include molecules that bear phosphorus, like phosphine, because we're just like, well, why would you ever find a molecule there? That's not present in our solar system. Why would we expect it in our next solar system? And it might just be that we've been being a little bit closed-minded, that we should be thinking about phosphorus photochemistry in other planetary environments. So first, we have to if phosphine is really there, it means that we have to include phosphorus in all of our thinking about rocky planets, which is new, and their atmospheres are rocky planets. Another really exciting idea is that here on Earth, in the oceans, phosphorus is the limiting nutrient. If you add phosphorus to a patch of ocean, you get more life there. Like it is this thing that controls the abundance of life in the oceans and hence on Earth and overall more than anything else.
It's also super important. It's present in DNA in huge amounts, and it's all over the place. It's a
basic nutrient.
Yeah,
and people have been saying for a while now that phosphorus is going to be rare on Earth. It's going to be even rare on some of these exoplanets, planets orbiting other stars. In particular, these water worlds. Phosphorus is going to be, they're arguing, is going to be super rare in water worlds because the water worlds won't have continents, and you won't have the phosphorus source from continents that you have here on Earth. if it turns out that Venus is a phosphorus-rich environment, and according to some of the data from these Vega landers, there could actually be quite a bit of phosphorus, probably most of the present as phosphate in the atmosphere. Maybe that suggests, I'm just spitballing here, I haven't done any kind of real calculations on this. Maybe that's suggesting that phosphorus isn't as rare on some of these planets, and we shouldn't be as down on some of these water worlds as potential venues for life. So, yeah, for me, it's just hinting at the possibility of phosphorus-rich terrestrial planets, which is not something I thought about, and I think if it bears out, then it's something we need to think about.
Yeah, most of us didn't think about that. And I was going to ask you, but because we are coming to the end of the show, is there anything else you would like to talk about?
He promised us a taste of what he's going to come up with next.
Yes.
What do you got to tell our audience?
Well, I was just, it's actually, I let the cat slip the bag a little bit already. I was really excited about those mass spec measurements from the old American Pioneer probes.
Oh, okay. Yeah.
And yeah, so that's what I was just really excited about, in the sense that it's a potential test of whether or not phosphine is there, using a totally different method.
Yeah.
So with our telescopic observations, we use two different telescopes at two different places, with two different methods of detrending the data, but we were still only looking at one spectral feature, and so we were still vulnerable to errors derived that come from that assumption. This is potentially a totally different method using in situ observations to test this. And we talked to the team there, and the team was actually super skeptical. They didn't really go in expecting to prove or disprove our report. And just from their interpretation of the data, they think that phosphine being there is the most natural interpretation. So obviously, mass spec is a really complicated area. I'm really excited to see where that goes, because that data is there already. You don't have to spend a lot of money, a lot of resources. You can just look at it and see whether or not you believe it.
Yeah.
Okay.
Yeah, that's great. And do you have anybody to plug? Any shout outs? Are you going to be working on a book in the foreseeable future?
Or your own research?
Yeah.
No, all of us are just continuing our own individual research trajectories, of course, with bearing in mind this work. I think all of us are just excited to see the scientific method proceed. I continue to do my work. Everyone else continues to do theirs. And we're just right now, I think it's a little bit of wait and watch. We've released a bombshell on the scientific community. Let folks process it. Yeah. Our methods are public. Our data is public. Let's see where it goes, and let's see what we can learn from it.
Okay. I have one last real lame question. You're going to hate it, but does your gut tell you that there are microbes in the cloud bank of Venus making this stuff?
My gut tells me that it's dangerous to trust my gut for anything other than dinner.
He's so much more a scientist than I am. I love it. I love you, man. That's great.
Well, Sukrit, thank you so much, man. I really appreciate you being with us today. I think, us and the listeners really benefited from having you on, and we really do appreciate you being here.
Thank you again, Sukrit.
Yeah, thanks for being on our show.
Thanks so much for the opportunity. Hope you all have a really great day.
You have a good night too.
Okay, we'll see you next week on Science Nights in the Morning. Thanks for listening to this episode of Science Nights in the Morning. Be sure and follow us on Patreon for exclusive gear and uncut episodes. Check out the latest science articles on our Facebook page and subscribe to us on YouTube and your favorite podcast listening app. You can also listen every Saturday at 10 a.m. Central Standard Time at BigBenRadio.com. And if you got a question, we'll join the discussion. Hit the hotline at 432-217-1983 and record your message. We couldn't do this without you, and thank you so much for listening each and every week. That's Science Nights in the Morning with a K, and we'll see you next time.